In this video, we will introduce the definition of the derivative. In parentheses here, I've written as h approaches 0, and the reason why I'm including that is because there are two forms for the definition of the derivative, and in this video we'll look at one of them, in which we take the limit as h goes to 0. Alright, so in the last section, 3.4, when we talked about average and instantaneous rate of change, we drew a picture like the following. So let's say that we have our axes, and then I draw some function. So I want to draw some functions graph. And on this graph, what we did is we took some point. Let me just label it A. And let me call this, so my function, let's call this f of x. So this point right here would be a comma f of a. And then what we did is we wanted to estimate the instantaneous rate of change at that point. In other words, the slope of the tangent line at that point. And we did so by taking a nearby point. So maybe let's call this a plus h. And a plus h could either be on the right side of a, or it could be on the left side of a, if the h happened to be negative. But if it was like this, if we connected these 2 points, we get a line like this. And this line is called the secant line. And as we let h get closer and closer to 0, this secant line approaches the tangent line. And the tangent line sort of represents how steep the graph is right at that point. So we want to draw the tangent line in such a way that it represents how steep the graph is right at that point. Okay, so this is the picture that we had from section 3.4. Okay, so let's remind ourselves what we were doing here. We were trying to compute the slope of this tangent line at x equals a. Oops, I should label one other thing. I should label this other point. So its x coordinate was a plus h, and the y coordinate is f of a plus h. So we're interested in finding the slope of the tangent line to the function at x equals a. So the way we did that is we took this average rate of change slope, which was f of a plus h minus f of a, so that's change in y on top, over the change in x. But when we subtracted these two x values, a plus h minus a, we just got h on the denominator after we simplified. And the way we make it the slope of the tangent line and not the secant line is we have to make that h get closer and closer to 0. So we took the limit as h approaches 0. So this slope of the tangent line is called the derivative of the function at a. And it's written f prime, that's how we say that apostrophe, f prime of a. So this formula is what I'm going to call the derivative, but the derivative at just one individual point, at whatever a happens to be. In these two sections, 3.5 and 3.6, we're going to look at a similar scenario, but now instead of just getting the derivative at one individual point, I'd like to get the derivative as a function. So keeping a variable inside the parentheses here. So I'm again going to draw just my picture of my function. So I'm doing my best to make those look identical, but bear with me if they're not quite identical. So now instead of calling this a, whatever the number a is, I'm going to keep it as a variable, as x. So this would be x comma f of x. Oops, close that parentheses, and then I'll take something kind of close to x. And again, it could be on the right or on the left of x, doesn't really matter. Technically, I do need to consider both. And then take the limit as h goes to 0. So when I take the limit as h goes to 0, h could be positive, which means this number would be on the right side of x. Or it could be negative, the h could be negative, in which case x plus h would be on the left side of x. So it could be on either side of x. So if we connect these with the secant line, it looks the same as what we had before. And I could draw the tangent line, just as we had before. So we could draw the tangent line. So this pink one was the tangent line. And the blue one was the secant. Blue one was the secant line. All right. So what I want to do now is, I want to take the limit that we had before. The limit is h approaches 0 of f of x plus h minus f of x all over h. So now, instead of having a specific number, like a, being plugged in, I'm going to keep it as an arbitrary variable, x. And when we do that, this is what we're going to define f prime of x to be equal to. Okay, so this is the definition. I'm just going to abbreviate definition. Definition of the derivative. That's how the derivative function is defined. So this is called the derivative of f of x, and it's written f prime of x, or there's another notation that we'll see, which is we write df dx. So we'll see that a bit later. But this is the derivative as a function. It's in terms of x. All right. So there are two key facts that I want to state about this derivative function before we do some examples or using this definition of the derivative. So the two key facts involve what the derivative represents. So f prime of x represents the slope of the tangent line to the function, to f, at whatever x is. So whatever we plug in for the x, f prime of x will represent the slope of the tangent line to the function at that x value. The other thing the derivative represents is the instantaneous rate of change, which we've been abbreviating as IROC. Instantaneous rate of change of f at x. Remember, the instantaneous rate of change, that was just the slope of the tangent line. Average rate of change was the slope of the secant line. All right, so let's look at an example. So let's let f of x be the function 3x squared, and let's find f prime of x, that means the derivative, using the definition of the derivative. Okay, so when we do it using the definition of the derivative, this means no shortcuts. No shortcuts. So if you've seen derivatives before, you might have learned rules such as like the power rule or product rule and quotient rule and all these rules. So those are a bunch of shortcuts for doing derivatives, but we are not quite there yet. We haven't learned those shortcuts. Those will come later. So at this point, we want to be using just the definition of the derivative to evaluate this derivative. Okay, so f prime of x. Our definition says it's the limit as h goes to 0, f of x plus h minus f of x over h. So simplifying this, we get the limit as h goes to 0. Well, actually first, let's evaluate it. So first I have to plug in x plus h in for the x. That gives me 3 times x plus h squared. And then minus f of x. So that's minus 3x squared. All over that h in the denominator. Okay, so we have this. The next thing that we're going to need to do is this x plus h squared. Let's expand that out. Let's FOIL that out. X plus h squared is x plus h times x plus h. And multiplying that out, that's x squared plus 2xh plus h squared. All right, so I'm going to continue my work at the top of the page. Okay, so we have that this equals the limit as h approaches 0 of 3 times x squared plus 2xh plus h squared minus 3x squared over h. And this equals the limit as h approaches 0. Now I can distribute the 3. we get 3x squared plus 6xh, plus 3h squared minus 3x squared all over h. Okay, so something nice happens in the numerator. There's some cancellation. So we have this 3x squared and the negative 3x squared, they cancel. And I can do a little bit more in the numerator now. I have the limit as h approaches 0. I can also factor out an h, because that's common. If I also wanted to factor out the 3, I could. It'll turn out factoring out the h is the most important one, because that'll cancel with the h in the denominator. So I'm just going to factor out h. Okay, so when we do that, we're left with 6x plus 3h over h. And now there's some more cancellation. This h cancels with that h. So we get that this equals the limit as h approaches 0 of 6x plus 3h. Now we are good to plug in. What was stopping us from plugging in before was when we plugged 0 in before, or if we tried, we had the 0 on the bottom. And that was a problem. But once we've simplified and once we cancel that h out from the bottom, now that issue is gone. So we are good to plug in. So we get 6x plus 3 times 0 when we plug in, which is just 6x. And that's my derivative. So thus, f prime of x, the derivative function, is 6x. All right, so I want to ask a follow-up question about this. So part B, what are the slopes of the tangent lines to f at these x values, 0, 1, and 2? All right, so because it's asking for the slopes of a few different tangent lines, let's keep track of this in a table. So I'll keep track of x and the slope of the tangent line in a table. Okay, so I'll keep track of 0 and 1 and 2. Okay, so let me also just draw a picture of our function. So I'll draw some axes and I'll draw a rough picture of our function. So our function was 3x squared, remember. That was our original function. F of x equals 3x squared. And that's an upward facing parabola that has a vertex at the origin. And what a 3 does is the 3 in front sort of stretches it vertically by a factor of 3. Okay, so what we want to know is, well, what's happening at x equals 0, what's happening at x equals 1, and what's happening at x equals 2 in terms of the tangent lines. So we know that to get the slope of a tangent line, I take the x value and I plug it into the derivative, because that's what the derivative tells me, the slope of the tangent line at that point. So with 0, I'll plug 0 into my derivative, which gives me 6 times 0, which is 0. And in terms of the picture, if we look at where the point is on the graph, where x is 0, if we think about drawing the tangent line there, what does it look like the slope of the graph is right at that bottom point? Well, it looks like right at that bottom point, the graph gets momentarily flat. And that's what the tangent line also will look like. It is also just flat. So, and a horizontal line like this has a slope of 0. And that matches up with the fact that we are seeing that our derivative ended up equaling 0. So that's good. So let's do these other values. If I plug 1 into the derivative and look at f prime of 1, we'll get 6 times 1, which is 6. Okay, so that's the slope of that next tangent line. Plugging in 2 into the derivative, we get f prime of 2. So 6 times 2 is 12. So let's draw in these tangent lines as well to see if these numbers just make realistic sense. So when we take the tangent line at 1, so here's the point on the graph where x equals 1, and if we draw the tangent line, and again, I have to draw the tangent line in such a way that right at that point, it sort of mimics how steep the graph is. So it touches it ever so slightly. Okay, and the slope of that green line that I've just drawn is definitely a positive number. It's bigger than 0 for sure, because 0 was a flat slope, sort of a flat line. So it's good so far. What about if we draw that third tangent line, the one at x equals 2? So when x equals 2, we would have a tangent line that looks more like that going up and like this going down. So that is the tangent line at x equals 2. In fact, let me even label that. This one is the tangent line at the point 2 comma f of 2. That's what this point right here is. This is 2 comma f of 2. F of 2 means whatever the y coordinate is at that point. So looking at these slopes, the 0, the 6, and the 12, these slopes are increasing. These are increasing slopes. They're getting larger the bigger x gets. And in terms of the graph, that matches up with what we see. This matches the graph. Because going from on the graph where x is 0 to where x is 1 to where x is 2 and looking at those respective tangent lines, they get steeper and steeper. So it makes sense that we're seeing that their slopes are getting bigger and bigger. All right, so let's do one more part to this example. So we've found how to get some slopes. What about if we wanted the equation of a tangent line? So not just the slope, but what if I wanted the full equation of the tangent line? Actually, one quick comment before that. So one thing I want to point out about part B, which is one of the reasons why it's good to have this derivative function is it's now easy to find the slopes of many tangent lines with this derivative function. Oops, I think I'm misspelling that. Derivative function. Because if I have the derivative function, like here, the derivative function of 6x, I can just start plugging in x values into that, like 0 and 1 and 2, and I get the slope right away when I do that. Before this section, the way we would get each of these slopes is I would do a definition of the derivative at a point for 0. So I'd set up that whole limit expression when x is 0. I'd have to do it again, the whole limit expression when x is 1. And then I'd have to do it yet again when x is 2. So having this general definition of the derivative lets me avoid having to recalculate the limit again and again and again each time I have a different point. And that makes it nice. All right, so now let's talk about part C. Let's get the equation of the tangent line to f at x equals 3. Okay, so this one, I want you all to try. Pause the video for 2 minutes and try this problem. 4, 3, 2, 1, pause the video. Pause the video for 2 minutes to try this. What's the equation of the tangent line at x equals 3? All right, so hopefully you've done that. Hopefully you've paused the video and really tried this. So the key thing is I need an equation of a line. It just so happens to be a tangent line, but for any line, to get the equation, we typically need the slope, and then we usually have a choice, either a y-intercept or a point, depending on which form of the equation of a line we use. But typically we've seen that it's easier to get a slope and a point. So the thing that tells us the slope is the derivative. In this case, it would be the derivative evaluated at 3. So we'd get 6 times 3, because remember the derivative f prime of x was 6x. That was our derivative. Plugging 3 into that, we get 18. And then what's our point? So the point on the graph is, well, we know that this tangent line happens at x equals 3. So the x-coordinate of the point is 3. And the y-coordinate, so remember the original function was 3x squared. The y-coordinate is going to be f of 3. So this equals 3, comma, and then f of 3 is going to be 3 times 3 squared, which is 3 comma 27. So finally, we are ready to write down the equation. It's going to be y minus the y-coordinate of the point, 27, equals the slope, 18, times x minus the x-coordinate, so x minus 3. Okay, so all the problem set is get the equation of a tangent line. which means it is absolutely okay to stop here. Point slope form is definitely an equation of a line. So of course, if you wanted to isolate the y and get it in y equals mx plus b form, we would end up getting y minus 27 equals distributing 18x minus 54. And then if we add the 27, we get y equals 18x minus 27. And that's what it would look like in slope-intercept form. So what I want to end this video with is by doing a Desmos demonstration to show what these tangent lines to functions look like. All right, so what we have here is I have Desmos. Oops, I'm gonna make that, okay, yeah. So we have Desmos, and I have the graph 3x squared drawn in. And this point, a comma 3a squared. So a comma 3a squared, that's just an arbitrary point on the graph. And I have a slider set up. So with a slider, if I move this around, it changes where the point is on my graph. Okay, the equation underneath that is actually the equation of a tangent line, just in the most general form. If I keep the x-coordinate a, so it's the same as the x-coordinate of this point, and I keep the y-coordinate 3a squared, so the same as the y-coordinate of this point, and notice that for the slope, I've taken the derivative equation, which is 6x, and I've just plugged in the x-coordinate. I've plugged in a. So if I make this appear, notice that this line has shown up, and that's the tangent line to the graph at that point. So if I start sliding this, the tangent line will move alongside it. So notice that at this bottom point, my tangent line is horizontal. That's because the derivative is 0. The slope of the tangent line is 0. And as it gets more and more positive, the slope gets steeper and steeper this way, and the opposite happens in the other direction. When x is negative, my slope is negative. And that matches up with what we see with the function 6x. Because when x is negative, the value of 6x is also negative, so it makes sense that we're seeing a negative slope like this.